Good day, kids. So today we're going to discuss systems of linear equations, applications of systems of linear equations. The course objective for this video would be to set up and solve a systems of equation to represent a network. Network analysis. Network composed of branches and junctions are used as models in such fields as economics, traffic analysis, and electrical engineering. As an application, you can see that for certain intersection, you can say that the number of vehicles going in must be equal to the number of vehicles going out. So the number of vehicles going in is equal to the number of going out. That is basically the principal concept of network analysis. In a network model, you assume that the total flow in the junction is equal to the total flow out of the junction. Let us solve this example. Set up a systems of linear equations to represent the network shown in the figure 1.6. Then solve the system. So we are going to consider each node, and the model that we are going to use is that the summation of elements going in must be equal to the summation of elements going out. So first, let us consider the first node or the first junction. For those going in, we have 20. And for the elements going out, we have x1 plus x2. For the second junction, the elements going in are or is x4, and the element going out is x3 plus 20. For the third element, we can have, or for the third junction, we can have x2 plus x3. And then for those going out, it would be 10 plus 10. For the fourth junction, going in, x1 plus 10, x1 plus 10, and going out, x5. For the fifth junction, going in is x5 and 10, and going in is x5 and 10, going out is x4. Now we can form a matrix coming from this equation, taking note that we're going to align x1, x2, x3, x4, x5, and then the constant. So for the first equation, we have 1, 1, and then the constant is 20. All other elements would be set as 0. For the second equation, we have x4 minus x3. So negative x3 plus x4 is equal to 20. So negative x3 plus x4 is equal to 20. All other elements would be set as 0. Equation number 3, 0, 1, 1, x2 plus x3 equal to 20. So 0, 0, 20. Next, 1, 2, 3, equation 4, we can have x1 minus x5 is equal to negative 10. x1 minus x5 is equal to negative 10. And finally, we can transpose x5 to the other side. So x4 minus x5 is equal to 10. And then all other elements would be 0. So with this systems of equation, 1, 1, 0, 0, 0, 20, 0, 0, negative 1, 1, 20, 0, 1, 1, 0, 0, 20, 1, 0, 0, 0, negative 1, negative 10, and 0, 0, 0, 1, negative 1, 10. You may wish to rewind this video so that you can go back to this equation. Proceeding, we are going to have this sets of equation. X1 plus x2 is equal to 20, x3 minus x4 is equal to negative 20, x2 plus x3 is equal to 20, and so on. With this, we are going to have the matrix equation, and we're going to find Gauss-Jordan elimination by finding the RREF of this matrix. So instead of finding the Gauss-Jordan equivalent, finding the reduced row echelon form, we can also perform some arithmetic manipulation. So we can have this one by back substitution. So we have x4 is equal to x5. So x4 is equal to x5 plus 10. Take note of this equation. We're going to plug it in here. Let's first set everything in terms of x5. So for this one, let's have x1 is equal to, let's transpose this to the other side. So that's x5 minus 10. So this is equation 1, 2, 3, 4, 5. So this is equation 4. This is equation 5. Now for equation 3, we can have x2 is equal to negative x3 plus 20. And then equation 2 is x3 is equal to x4 minus 20. However, we have an equation of x4, so we can have x3 is equal to x5 plus 10 minus 20. So we can say that x3 is equal to x5 minus 10. And then we have the first equation, x1 is equal to negative x2 plus 20. So x1 is equal to, what is x2? x2 is negative x3 plus 20. So we can now say also that x1 is equal to x3. x1 is equal to x3 basically. So x1, x4, x2, and then we have this x3 equivalent. But x3 is equal to x5 minus 10, so x1 is also x5 minus 10. So we have represented everything in terms of x5 except for x2. x2 is equal to negative x3 plus 20. So x2 is equal to x3. So negative of x3, x5 minus 10 plus 20. So x2 is negative x5 plus 10 plus 20, so plus 30. So we can now write everything in terms of x5. x1 is equal to x5 minus 10, x2 is equal to, x2 is this one, 30 minus x5, or negative x5 plus 30. For x3, x5 minus 10. For x4, we have this one, x5 plus 10. So as you can see, you can write everything in terms of x5, and we can let your x5 to be t. Of course, you can use the reduced row echelon form to simplify this. I think you have the capability of doing that already. So you can find the reduced row echelon form of the given augmented form of matrix, and then after that, we find this resulting systems, or a given solution. So we can now write x1 to be equal to t minus 10, x2 is equal to negative t plus 30, and x3 is t minus 10, and x4 t plus 10, while setting x5 is equal to t. With t is any real number, so that this system has infinitely many solutions. Now, if x1, x2, x3, and x4, and x5 must be greater than or equal to 0. So say, for example, the traffic cases. So we can say that t minus 10 must be greater than 0. So that's t greater than 10. We can also have negative t plus 30 is greater than 0. So 30 is greater than t. T minus 10 is greater than or equal to 0. So that's just this one. T plus 10 is greater than or equal to 0. So t is greater than or equal to negative 10. And t greater than or equal to 0. So for our solution, we are seeing positive 10 and 30. We want the number to be greater than or equal to 10. At the same time, t must be less than or equal to 30. And then it must also be greater than or equal to negative 10. And t must also be greater than or equal to 0. As you can see, the intersection of this region is from 10 to 30 inclusive. Now let's have another network applications. An electrical network is another type of network where analysis is commonly applied. An analysis of such system uses two properties of electrical networks, known as Kirchhoff's laws. All the current flowing into a junction must flow out of it. The sum of the products, IR, so take note that the voltage drop is equal to the current times the resistance, around a closed path is equal to the total voltage in the path. So we are going to use the Kirchhoff's laws. Summation of current in is equal to the summation of current out. And we also have the summation of voltage drops is equal to the electromotive force. So this is KCL, Kirchhoff's current law, and KVL, the second one is KVL, Kirchhoff's voltage law. In an electrical network, current is measured in amperes or amps. Resistance is measured in ohms, the Greek letter omega. And the product of current and resistance is measured in volts. So voltage is current times the resistance. For the units, voltage, 1 volt is equal to 1 ampere times 1 ohm. The symbol that we are going to use would be this two lines for battery. So there is a designation of the positive sign, the positive terminal and the negative terminal. The larger vertical bar denotes the current flows out of this terminal. So it goes out in this direction. And the symbol is used to denote resistance. An arrow in the branch shows the direction of the current. Determine the currents I1, I2, and I3 for the electrical networks shown below. So let's have first a designation for the current flows and then the junctions. So we have junction 1 and junction 2. Now we are going to assign currents that would be flowing to the nodes. So we can have this to be I1, this current is I2, and this current is, I2 is going into this direction and I3 is going to this direction. Now I just followed the designation given. So we usually use a counterclockwise direction for current. So the current flow would be I1 going in and I2 would be going out. While if we're going to have this loop below, so I3 is going in and I2 is still going out of the node. Now from KCL or Kirchhoff's current law, we have I1 plus I2 plus I3 is equal to I2. So I1 plus I3 is equal to I2. So we can have this one as I1 minus I2 plus I3 is equal to 0. Now we have to find the loop equation. So let's have path 1. For path 1, we have the voltage drops. So the voltage on R1 plus the voltage on R2 equal to the 7 volts. And for path 2, the voltage on R3 plus the voltage on R2 must be equal to 8 volts. So take note of some of our designation. So current must be going out of the longer line. So that is why we have 7 volts and 8 volts respectively. So positive 7 and positive 8 because the current goes out to the side where current should go out. Now for the voltage drops, VR1 plus VR2 is equal to 7. So the voltage here plus the voltage here must have a total of 7 volts. Now we're going to have the product of current times the resistance for that. So taking note of this equations, we are going to have I1 is equal to I1 plus I3 is equal to I2, while VR1 plus VR2 is equal to 7 and VR2 plus VR3 is equal to 8. Now since we have the 3 ohms and the 2 ohms resistors, wherein current I1 and I2 would pass through, we are going to have 3I1 plus 2I2 is equal to 7, and 2I2 plus 4I3 is equal to 8. So we can have the systems of equation being written as 1, negative 1, 1, 0. 1, negative I2 plus I3 equal to 0. And then we have 3, 2, 0, 7, and 0, 2, 4, 8. So to solve this equation, I think it's better to um, do row echelon form. So this is row 2 minus 3 times row 1 and place the answer as row 2, while we multiply 1/2 to row 3. But I want to interchange the result. So maybe we can interchange the result later. So we can have R2 minus 3R1 and place the answer as row 2. And 1/2 row 3 is equal to row 3. So we copy it as 1, negative 1, 1, 0. 3 minus 3 is 0. 2 minus 3 times negative 1. So 2 plus 3 is 5. 0 minus 3 times 1 is negative 3. 7 minus 3 times 0 is 7. And then we have 0, 1, 2, and 4. I want to interchange these two rows so that I would be having 1, negative 1, 1, 0, and then 0, 1, 2, 4, 0, 5, negative 3, 7. This is just to ensure that we have a leading one as the pivot row. So row 1 plus row 2, and then we place the answer as row 1, and then we have row 3 minus 5 row 3 and place the answer as row 3. So that would be, we add, so 1 plus 0 is 1, negative 1 plus 1 is 0, 1 plus 2 is 3, 0 plus 4 is 4. And then we have 0, 1, 2, and 4. 0 minus 5 times 0 is 0. 5 minus 5 times 1 is 0. Negative 3 minus 5 times 2 is negative 13. So that's negative 3 minus 10 is negative 13. 7 minus 5 times 4. 7 minus 20. 7 minus 20 is negative 13 as well. So we can divide this by negative 13. Saktong-sakto. So we can have 0, 0, 1, 1. Take note of these values. So 1, 0, 3, 4, 0, 1, 2, 4, and 0, 0, negative 13, negative 13, or 0, 0, 1, 1. So let's have the next slide. So the given systems of equation resulted into this. And then after that, we find the row echelon form. So the answer would now be I1 is equal to 1 ampere, I2 is equal to 2 amperes, and I3 is equal to 1 ampere. So that's all. Thank you for watching.